Welcome to the deep dive. Today we are taking a closer look at, well, at nothing.
Yes.
But not, nothing as in the absence of things or just the space between stars. We're talking about maybe the biggest conceptual bait and switch in the history of physics, the vacuum itself.
It's really one of the most astonishing conceptual shifts.
Mm.
For centuries, if you asked what the void was, they would have described it as, well, just a passive, inert container.
A box.
Right, a box.
Yeah.
Classically, going way back to Aristotle, empty space was just defined by the complete absence of stuff.
Right. It was what it wasn't. It was just the stage. But then quantum field theory, QFT, shows up in the 20th century and basically tells us the stage is alive.
Exactly. The quantum vacuum isn't empty space, it's a plenum. It's this continuous, dynamic, and incredibly complex foundation for everything.
So that's our mission for this deep dive. We're going to unpack how QFT totally redefined this idea of nothing.
And look at the incredible experiments that prove it's real. And then tackle the catastrophic problem its energy creates for the entire universe.
Okay, so let's start there. The definition. If the classical void was just an absence of matter, how does QFT define its vacuum?
The quantum vacuum is formally defined as the lowest possible energy state of all the quantum fields that permeate all of space-time.
Okay, wait.
In the math, in the what's called Fock space, it's the state where you have, let's say, no real observable particles.
Lowest energy state. So
Yeah.
shouldn't it be still quiescent? Where does all this activity come from if it's at rock bottom, energy-wise?
It comes from the rules of reality itself. It's mandated by, specifically, the Heisenberg uncertainty principle. That principle basically says you can't have it all. A quantum field cannot simultaneously have a perfectly defined value and a perfectly defined rate of change. You just can't nail both down at the same time.
So it literally cannot sit still. Even at zero energy, it has to fluctuate.
Precisely. This inherent quantum fuzziness means the field's energy is constantly jittering around zero. And these fluctuations, they manifest as fleeting disturbances we call virtual particles.
Virtual particle.
Yep. Particle-antiparticle pairs that just burst into existence, borrow a tiny bit of energy from the vacuum, and then poof, they annihilate each other almost instantly.
Okay, but if they vanish before we can directly observe them, they sound a bit like ghosts. How do we know they're not just a mathematical trick?
They're ghosts that leave very real fingerprints. They exist for such a short time that they sort of get to bend the rules of energy conservation, but because they're constantly popping in and out of existence everywhere, they create this churning, dense cloud that interacts with everything that is real.
And what did that constant interaction do to the early calculations in QFT?
It was a complete disaster at first.
Yeah.
When people like Feynman tried to calculate the influence of this infinite sea of virtual particles on a real particle, like an electron,
The math just broke.
they ran straight to infinity. The sums diverged. Every answer was infinite.
So the idea that everything we can measure is being perpetually bombarded by the void it blew up the equations.
It did. You couldn't ignore it. But when you tried to account for it, the results were useless. The solution was a very clever technique called renormalization.
This always sounds like sweeping the problem under the rug. What is it actually doing?
It's less of a trick and more of a redefinition. Instead of trying to calculate the theoretical bare charge or math of an electron, which is an impossible task,
Because it would include this infinite interaction.
right? We just redefine what we mean by mass and charge. We accept that the values we measure in the lab already include that infinite interaction with the virtual particle cloud.
Can you give us an analogy for that?
Sure. Imagine trying to weigh a bowling ball that's at the bottom of the ocean.
Okay.
The water is constantly swirling around it, affecting your measurement. Renormalization says, forget the theoretical dry mass. It's unknowable. All we can ever measure is the wet mass. So we just define that wet mass as the real mass and work from there.
That's fascinating. So you're just accepting that the vacuum is this active medium, and we can only ever measure things inside it?
Exactly. And the incredible success of QED quantum electrodynamics, which is built on this idea, proved it was more than just a fix. It was describing reality.
So speaking of reality, let's get to the hard evidence. When did this idea of an active vacuum become, an irrefutable empirical fact?
The proof really rests on two cornerstone experiments. The first was the Lamb shift, back in 1947.
With Willis Lamb and Robert Rutherford.
That's right. And this all has to do with the hydrogen atom, the simplest atom, which everyone thought they understood perfectly. Based on Paul Dirac's theory at the time, two specific energy levels in the hydrogen atom the 2s and 2p states, should have had the exact same energy.
He should have been identical degenerate.
Exactly. But what Lamb and Rutherford found was that they weren't. There was this tiny but very definite energy difference, a shift of about 157 megahertz.
And no one expected that.
No one. And the cause was the quantum vacuum.
How? What was it doing to the atom?
The electron in the hydrogen atom is constantly interacting with the zero-point fluctuations of the vacuum. It's being jiggled, essentially. This jiggling smears out the electron's position a tiny bit.
Okay.
And because the electron in one of those states, the s state, spends more time right near the nucleus, that smearing has a bigger effect on its energy. And that tiny difference is the Lamb shift. It was the first solid proof the vacuum was physically doing something.
Wow. And that brings us to what's often called the most accurate prediction in all of science.
Yes, the anomalous magnetic moment of the electron. This is really where QED just knocks it out of the park.
So Dirac's original theory predicted the electron's magnetic property, its G factor, should be a clean, simple number.
Exactly, two. Just number two.
But it's not.
It is not. QED, with its cloud of virtual particles, predicted a tiny, tiny deviation from 2. That deviation is the anomalous part.
So the calculation is literally what a real electron interacting with a virtual photon that pops out of the void and then pops back in.
That's the simplest interaction, yes. To get the modern precision, you have to calculate tens of thousands of these kinds of interactions using Feynman diagrams.
And the experiments.
The experiments are incredible. They trap a single electron in a device called a Penning trap and measure this property to more than 10 significant figures.
And the theory matches the observation.
It matches to something like 1 part in a trillion. It's the most stunningly accurate agreement between theory and experiment in history. It's quantitative proof that the vacuum fluctuations are real.
So, okay. The scientific consensus is absolute. The vacuum is not empty. It's a seething sea of energy. But this incredible success story is also the source of the single biggest crisis in modern physics.
It is. This is where we have to connect our theory of the very small, QFT, to our theory of the very large, general relativity.
Because according to Einstein, any form of energy is a source of gravity.
Any form. So this constant churning zero-point energy of the vacuum. It should have a huge gravitational effect. It should behave just like Einstein's cosmological constant.
Which we now believe is dark energy, the repulsive force that's accelerating the expansion of the universe.
Right. So the vacuum seems like the most natural candidate for dark energy. It should be what's driving the expansion. The problem, the crisis, is the numbers.
The magnitude.
The catastrophic mismatch in magnitude.
Let's break this down because this is where my brain starts to hurt.
Yeah.
What does our best theory, QFT, predict for the energy density of the vacuum?
If you sum up all the contributions from all the quantum fields, even if you're being conservative, the theory spits out a truly gargantuan number.
And that number is?
It's around 10 to the power of 112 ergs per cubic centimeter. That's what the vacuum's energy density should be.
10 with 112 zeros after it. Okay. Now, what do our telescopes, our observations of the expanding universe, actually tell us the number is?
What we actually observe is about 10 to the power of minus 8 ergs per cubic centimeter.
So 10 to the 112 versus 10 to the minus 8. That's a discrepancy of, what, 120 orders of magnitude?
Yes, 10 to the power of 120.
That's not an error. That's not even wrong. That's the definition of a theory completely failing.
It is famously called the worst theoretical prediction in the history of physics.
Yeah.
It's a complete breakdown. It tells us we are missing something absolutely fundamental about how QFT and gravity connect.
It's like we understand perfectly how the vacuum works on a local scale in a lab.
With stunning precision.
But the moment you zoom out and apply that to the whole cosmos, the math becomes utter nonsense.
It forces you to wonder if there's some deep hidden symmetry, some unknown principle of nature that is forcing all these huge energy contributions to cancel each other out almost perfectly.
Leaving just this tiny, tiny leftover scrap that we see as dark energy.
Exactly. So the takeaway here really is that nothing is maybe the most important thing in everything. It's this dynamic foundation of reality.
It mediates forces, it gives particles mass through the Higgs mechanism.
And maybe most disturbingly, its stability governs the fate of our universe. Because there's this final provocative thought that the sources bring up. That the state of the vacuum we currently live in is likely not the true final ground state. It's probably a metastable state.
A false vacuum? I've heard that term. What does that actually imply?
It implies we're living in a valley, but it's not the lowest valley on the map. There's a deeper, more stable state, a true vacuum, that we're separated from by an energy barrier
So our vacuum could decay.
through a process called quantum tunneling, yes.
Yeah.
A bubble of the true vacuum could appear somewhere in the universe.
And that bubble would expand at the speed of light, just changing the laws of physics as it goes.
Precisely. As that bubble wall passed over us, the fundamental constants, the masses of particles, the strength of forces, it would all change. All existing structures would be instantly annihilated.
So the very ground state of our existence might be living on borrowed time?
The calculated lifetime is, extraordinarily long. We don't need to panic. But the fact that it's even a possibility tells us that the question, what is nothing, leads directly to the question of what is everything and how long does it last?
The solution to that 10 to the 120 problem isn't just about a new particle. It's about rewriting the fundamental rules of reality.
It absolutely is.
Something to think about next time you look up at the seemingly empty night sky. Thank you for joining us for the deep dive.